Thank you. Yes, well, we are arriving to the end of my lectures. Okay, so until now we have, of course, we have to start in the first lecture introducing stability and this kind of problems where some small parameters appear multiplying some derivative in time. Okay, so call that kind of problem with different time scales. Yeah, we introduce an approach called the singular perturbation method in order to be able to study this coupled system in a simpler way than just looking at the problem directly. Okay, that's the idea. So, and then we study first some wave ODE system, okay, for which we prove that one of the system wasn't compatible to the singular perturbation method approach, I'll say like that, and the other system, the other wave system, for the other wave system, we can prove that in fact the behavior of the subsystems called the reduced order system and the boundary layer system tell us good information about the stability of the full original system when the parameter is small enough. Okay, that's what we have done until now. And then we start looking at the KdV equation. First at all, just for the single KdV equation, and we spent almost 2 lectures looking at the interior stability and the boundary stabilization of that problem. Okay, we are using most of that material today in order to deal with this system coupling a KdV equation with an ODE. Okay, so we will see different methods to study that. The problem that we're considering, okay, is the following one. We have on the top a KdV equation, okay, and we put this small parameter epsilon in front of the derivative of this KdV equation, okay. So we have on an interval 0L, we consider the same boundary condition that we have been considering in the past lectures, the main one, let's say like that, okay. So Dirichlet, homogeneous Dirichlet at both ends of the interval, and here on the right-hand side of the interval, on the Neumann boundary condition, we put a coupling. A coupling term A times Z, where C is solution of an ODE, okay? And Z is has this form like that, okay? So that can be seen as a feedback control law, well, where in fact the control is acting on the Neumann boundary condition of the KdV equation, and is kind of a proportional integral control, okay? Like something like this, okay? So here, of course, the parameter epsilon is supposed to be small, okay? And well, for the ODE, we have Z dot equals to this parameter B times Z plus this boundary trace of the derivative of Y at x equal to 0, okay? The term in red there, okay? So we have three parameters, A, B, and C, and epsilon, which is our already known parameter intended to be small, okay? But for this system, we can in fact study the stability directly, just doing some computations, okay? We can study directly for any epsilon and to obtain some conditions on the other parameter A, B, and C, okay? And of course, the second question is what happens if epsilon is small enough, okay? Can we get better conditions in terms of the stability condition for the subsystem that we already know that we are working with, okay? And of course, we know that this approach, one of the interests is not only finding conditions for stability, but there's a way to approach the time behavior of the full system using simpler one. Okay. So first of all, we are going to use this technique to this KdV ODE system, but I will explain you more or less how does it work for an ODE system. Okay. So let's start with a finite dimensional example here, having a similar structure of our system, okay? Just to see what's going on. So we're consider two ODs, okay? Epsilon y dot equals to ay plus bz, okay? And z dot equals to cz plus dy, okay? And well, here, for instance, we can look at the first equation, okay? We impose a less than 0, so we know that the first equation, if we erase the coupling, okay, if we put b equals to 0, it's just a very simple system that we know that the system is asymptotically stable, okay? If in the first equation we put b equal to 0, okay? And so we know that in that situation, the first system will be exponentially stable and have a Lyapunov function as the first part here, something like y squared, okay? Yeah? So at this kind of approach, in order to build a Lyapunov function for a system where we add a second equation as the one for z, okay? It comes from a paper by Mazeng and Prali in '96, okay? And a more general method called the forwarding approach, okay? And so the idea is to, once we have one equation which is already stable, and we couple it with another one in this way, you know, the right way of considering z in your Lyapunov function is something like that, okay? And to find this new parameter m such that everything works well, okay? There is a more general framework, but for this example, we can see like this, okay? So for this system, we're using this Lyapunov approach, and well, the good thing is that then for the KdV equation, we're also using this, okay? As one of the main ingredients for our KdV OD system. Yeah? So here, some computations, okay? So with this Lyapunov function at hand, we just derivate with respect to time. We obtain v dot equals to what? All this term. Well, we know that we have to be able to recover again v with a minus something, okay? Somewhere, okay? So here, well, in this particular example, it's very simple to choose appropriate m just to eliminate one of the terms here. We choose m, capital M, such that m times a is equal to d, just to eliminate one of the, well, one term giving us some cubic term there, okay? The terms in y, yes. And with that, that capital M, we obtain, well, the second equation for v dot, okay? And then, as usual, we can just use jump inequality and some tricks here and there, okay, to introduce some free coefficients alpha 1 and alpha 2 in order to try to make this put this in the right form that we want for stability, okay? Here at the end of the day, we obtain v dot with a coefficient on y squared and a coefficient with z squared. Okay, so we want these two coefficients in front of them be negative. Okay, yes. So here we can, we haven't choose alpha 1 and alpha 2. Okay, so for this particular system, we can deal with this Lyapunov function, and at the end of the day, we obtain that this, well, this is the same shape that we had before. Okay, but here we can start looking at the conditions on the coefficient, okay? So remember that a is negative here, so we can always choose alpha 1 and alpha 2 small enough such that the change of the blue term is still negative, okay? The sign of this term is still negative. And then in the other coefficient, well, we can see that like a quadratic polynomial, and we can get some conditions on the parameters on the equation in order that we can choose in an appropriate way the coefficient base B, C, and D in order that to get in order we get an exponentially stable system, okay? Made by hand. Okay, so the question here is that what happened for this, again, for this particular finite dimensional system, if we assume that epsilon is sufficiently small, what happened? Okay, so we know we have done this in this week, okay, starting on last Friday. Okay, in this situation, we can follow the steps of this singular perturbation method to see what's going on, okay? So we're going to obtain the reduced order system, okay, and the boundary layer system, the slow and the fast dynamics, okay, in order to see what happens. Of course, we already know how we can obtain this system for this particular example. Okay, so the system is put in there. So for the reduced order system, again, we assume that epsilon is equal to 0. Okay, they allow us to obtain y in terms of z. Here, very explicitly, y equal to minus b over a z. Okay, and that's what we call the quasi-static solution. Okay, then we replace in the other dynamic, and we obtain a very simple system here for z dot. Okay, this is the way that we obtain, and we have here a clearly condition on the coefficients c minus bd over a have to be negative in order that the system is exponentially stable. Okay. And on the other hand, for the boundary layer system, okay, we change the time from t to tau, okay, which is t over epsilon. We define this y bar as y minus the quasi-static solution, who was minus b z over a, so we get this y bar, okay, and we can compute the equation for y bar. We obtain that, and at the end of the day, we take again epsilon equal to 0 just to simplify this method, and we obtain this other boundary layer system here in red. Okay? So we have here both. Okay? So for each subsystem, we have very simple conditions depending on the coefficient in order to have that both subsystems are exponentially stable. Okay? So here, well, can we assure using these two conditions that the system, the original full system is asymptotically stable? Okay. In order to do that, well, of course, we center again the system around this quasi-static solution. Okay, and we write this system which is equivalent to the previous one. Okay. And we obtain that. And we can perform an asymptotic and Lyapunov analysis again using the same function as before. Okay? Yeah? And well, here you can trust me. I hope we can do all the computations and see that in fact these two conditions are enough in order to get the exponential decay of this system when epsilon is small enough. Okay, so that's nice in the sense that here the condition for the reduced order system and the boundary layer system to be stable, make sure that you're going to get for epsilon small enough a system which is the original system which is stable. Okay, we get here the energy for V. And of course, this is a little more general, okay? When we have, again, infinite dimensional system, we're not going deeper in that. It's just to mention the result. Here we have the same structure of system, but they are not a scalar equation. They are systems. They're capital A, capital B, capital C, and capital D are now matrices, okay? With the appropriate dimension, of course. And there is a result, okay, that we can find in this very nice book by Kokotovich, Khalil, and Riley, okay, singular perturbation methods in control, okay, where in fact when you obtain this reduced order system and this boundary layer system, you obtain a stability condition, and they are good enough in order to obtain a stability of the original full system, of course, when epsilon is small enough, okay? And of course, there are other nonlinear versions, as I showed you before in other lectures. So that gives us the idea of how to, for this particular system, how to build a Lyapunov functions, okay, a Lyapunov function for this KdV ODE system. Okay, so going back to the system, to the main system we're interested in today. So we have, again, remember the KdV equation with a fast, we can say like that, a fast KdV equation with the other OD for C, okay? Of course, what happened here, okay? We, for instance, having in mind the example, okay, just before the first equation in the example was already stable. That's the reason we imposed the coefficient A to be less than 0, okay? Here, what is the situation if we consider that there is no coupling? Where here, if we look only at the KdV equation, okay, we put the coefficient A here, 0, yeah? What is the situation of that system? Okay, we know we look only to the KdV equation without the term AZ, okay? We know that this system has no interior damping, okay? And so there will be some solution conserving its energy if we are in a critical domain. If we are not in a critical domain, all the solutions are going to 0 in an exponential way, without interior damping, just like that. Okay, we know that. And the proof, I remember, was we write the energy, del2 energy, we made the computations, we obtained that the derivative of the energy is less or equal to 0. So we call that a weak Lyapunov functions, okay, Lyapunov function, in the sense that in the literature, normally a strong Lyapunov function or just a Lyapunov function is something giving you the exponential decay of the solution to 0. So V dot less than minus something positive times V. Okay, here we know that we don't have that, we have like a weak Lyapunov function for the decay. In fact, I remember we proved the decay of the solution by using this V dot expression, okay, and then we use the observability inequality, okay, and we see that the energy of the solution for a time t+1 is less than a constant, less than 1 times the energy in time t, okay, and we know that when that happens, so we can get an exponential decay of the energy, okay, by building this interval by interval, time interval by time interval arguments, using this kind of semi-group properties, okay? So here the situation is that, so first of all, in order to have a stable KdV equation, we have to be in a non-critical situation here. Okay, first step, we impose that the domain L is not critical. But we will need, or at least we will be able to prove that everything works fine, but we need a Lyapunov function, okay? And for this KdV equation, we don't have one. We just have this weak Lyapunov function, okay? Well, I was telling you the things that are here in this slide, okay? So for that system, well, we know that in red it was the expression that I was telling you, okay, about the derivative of the time derivative of the energy, and we really like to have a strict Lyapunov function, okay. And so what is very nice for us is that in this paper by Balogun, Marx, and Astolfi, okay, in that paper they built a Lyapunov function for our problem, okay, exactly what we need. And in fact, there is this, this is a mistake here. I have to correct. It's not a stratification, it's a strictification, in the sense that it's a method to make a weak Lyapunov function in a strict, transform a weak into a strict Lyapunov function. So it's a strictification, not a stratification. Okay, to make something weak, make it a strict Lyapunov function. Okay, so in here, for that system, they assume that L is not a critical domain, a critical value, sorry. Okay, we already said that, because if not, well, there is no hope that having a stable system. Okay, and so they prove that there exists a Lyapunov functional, okay, W going from L2 to L2, which is equivalent to the energy in L2, to the norm, okay? It's equivalent to the norm. And additionally, in fact, we have that derivative, the time derivative of this along the trajectories of the system satisfies this, okay? So remember that with just the energy, we have this. Well, sorry, we have this, okay? But with this method, they are able to give us a Lyapunov function like this one, which is the one that we need, okay? Very nice. In fact, in that paper, the main interest was having an input to state Lyapunov function, okay? In order to see what happened when we have some perturbations, and the final goal for them was to study some regulation problem, okay? So regulation is like stability, but tracking not an equilibrium point, but something else, okay? And so here we have our Lyapunov functions. So we will be able to do more or less the same as in the OD example with this Lyapunov function, okay? But this Lyapunov function is very interesting to look at, okay? So I will try to explain how does it work, okay? How does it work, the construction that they made for this Lyapunov function, okay? So the general idea from the paper by Prali, which is, well, not that old, 2019, okay? So 5 years ago, okay? Quite new, okay? So is, well, we know we have a weak Lyapunov functional, so trying to build an observer, okay? In that way, you obtain an observer, you obtain the solution of the observer is close to your solution, okay? And you try to have that this observer give you a solution, okay, which is, I will explain that better than that. So, and that the solution of the observer is linked to a system for which we have an Lyapunov function, okay? In terms here, in fact, they use the backstepping approach, okay, as we already did yesterday, okay, to this system. Yeah. Well, they're not using here the same transformation that we show, but they are using the transformation Van-Corona Lu. Okay. In fact, the difference was this kind of the name of the form of the transformation is Fredholm transformation, not a Volterra transformation that we did. Okay. The Volterra transformation is when you integrate between x and 1, for instance, in order to have the transformation. Here they integrate on the whole domain 0L, okay? And they are you arrive to a kernel equation, which is harder to deal with, okay? Because now the kernel is, as I told you, is defined on a square domain, but you have a delta function on the diagonal of that. So it's much more harder to obtain a good estimate for the solution. Okay, so here, this is the system, the KDV1, where we forget a little bit about the coupling with the ODE. We have just the KDV equation, and they are able to build this observer, okay, this white hat. Okay, well, as I told you yesterday, this observer, okay, is of course converging to Y and is built with this backstepping transformation. And so the Lyapunov function W, okay, that they're gonna use for that is the energy, I forget, yeah, there is a coefficient there. The energy, Y, for Y, so that give us this boundary trace term, okay? We know that this is the weak Lyapunov function, and we add this term, the norm, the norm of pi of Y to the power 2, okay? Where, who is this operator, capital Pi? Is exactly the operator that maps the solution of this system. Okay, Y tilde is the system that you obtain when you do Y minus Y minus Y hat. Okay, Y tilde is the error. Okay, and so they are able to build in fact, this kernel Py here. Okay, P, the kernel P, in order to transfer the solution of Y tilde to the solution of gamma, of this equation gamma, where I just put the equation, the boundary conditions are the same, okay, as before. And now here, we know that for gamma, because we have this term lambda gamma here, this is, you know, this is one of the 2 lectures ago, we look at this system where we have an internal damping. Here's a constant damping, so a constant coefficient damping. So it's this here is very easily a situation in order to get the stability and the decay, the exponential decay of the solution. And here you obtain that the energy is a strict Lyapunov function. Okay, so the idea is, for the original system, we have a weak Lyapunov function, we have to add something, and the something that we add is related to this observer that we're able to build in order to match somehow the observer or the error with a system which is already exponentially stable, and we can obtain a Lyapunov function to prove it. Okay? So very, very nice deconstruction, and it's based on this strictification method by Prali. So it's very, well, Prali made it for finite dimensional systems, okay? So there were a lot of modification to get the results in this framework, okay? Okay, so we have now, thanks to them, we have now a Lyapunov function for the KdV equation for the linear with KdV equation with no damping when the domain is not critical. So we have to impose now that the domain is not critical, okay? Well, the first step, as for the finite dimensional example that we saw, is that we can prove that for any epsilon, there are some conditions on the coefficient in order that make the system exponentially stable, okay? And we can do that without singular perturbation method, because here epsilon is not small, it's any epsilon, okay? But we have our Lyapunov functions for the KdV equation. The Lyapunov function W, okay, is for the KdV equation, and using again the example and using this kind of forwarding method, we can add another part of to the Lyapunov function in order to take care of the Z dynamic. Okay, and so in the example, we put just a constant m that we choose as a over t or t over a, I don't remember, but it was just a constant, a real number. Here, in order, you see, we look at the Lyapunov functional, there v, the second term is epsilon, this cursive m y minus z, okay? And we are relating two things, a function y and a real number z. Okay, so this capital M, cursive M, is not a real number, now it's an operator. Okay, So but it's free to choose for us. So if we are able to choose a right operator capital M, cursive capital M, it's okay. Okay, and well, we can do the computation in order to have what we need. Yeah, and we can see in fact that the operator cursive M can be represented by an integral term, okay, with a function M. Okay, now we have a function capital M of x, and we need that this capital M of x is satisfied kind of a stationary KdV equation here. Okay. Yeah. Well, there is two ways of seeing that. There is well, we can see doing the computation that is exactly what we need in order that everything works well. Okay. If not, there is also some the equation that is satisfy M is called the Sylvester equation, something like that. And well, there is also a general framework in order to where these kind of equations appear. Well, and here we have that we can solve explicitly the system for M. So we can have this capital M, and so this cursive capital M operator in this way, okay? The capital M of x is given by minus z f of x, okay, where f satisfies the same equation but putting just minus 1 here, okay? And you can find this capital M like this, an explicit expression, okay? You can start derivating and seeing that everything works well. If not, please let me know, okay? Yeah. Okay, so the time derivative of the Lyapunov function, well, here, well, we already had this Lyapunov functional, W, but here, when we derivative with respect to time, we have the terms that we know that we will have, but here, because of the coupling, we obtain some terms in the bound, okay? But we were able to deal with the other part of the Lyapunov function, okay? We also have to derivate the other part of the Lyapunov functional. Okay, we have to derivate our Lyapunov functional. Just remember that there is two parts. I have this. I forgot. 2 parts. This epsilon W and this term with the cursive M. Okay. Here we have what happened with the derivative of capital W. Okay. And here we have what happened with the derivative of the other term involving this function M. Okay. Well, I'm not going to explain all this here, but well, of course, we introduce some coefficient here to do some Jones inequality in order to have some freedom to arrange at the end of the day all the terms in order to make that smaller than 0. Okay, so here we obtain, as previously, okay, this form for V dot. It's like the same that we had for the example, for the ODE example, okay? Here, well, we have to be careful in order to choose in the right way the coefficients in order to have an exponential decaying system, okay? Of course, we have to take care but separate on the blue term here being negative, so alpha has to be small enough. And then for the red term, we see it like a second order polynomial, and we are able to choose to make some room in order to put the right coefficients in the right place. Okay? Okay. So that, and for a small epsilon, here we are trying our singular perturbation method to the table. Okay, so we have again, of course, the same system. There's no changes. Okay, and our theorem for that was for any ABC such that B minus AC is less than 0, which is the condition for the subsystem be stable. Okay, we're gonna see that. We can prove that the system is globally exponentially stable. This is a linear system, exponentially stable for any epsilon is small enough. Okay, as we have already done several times during these lectures. Okay, and so in order to prove this, we're finally applying the singular perturbation method to this KdV ODE system. Okay, so as before, so we put epsilon equals to 0, we obtain a system, okay, which is this one. And again here we can, using the same function m that we saw before, okay, this is the same system, okay. So there exists a solution H, now depending on time, through this constant Z, okay. So here we have, again, the explicit closed form for this function f, okay? So, and then replacing under the equation, we obtain what we have called the reduced order system, z bar dot equals to, here we obtain b minus ac times z bar, okay? So here we see that this subsystem, the reduced order system, in order to be stable, has to satisfy this condition, which is the final condition for the couplet system. Okay. Of course, for the boundary layer system, we do again this change of time. Okay, and we obtain what we already know very well. That is the linear KdV equation with no damping, with homogeneous boundary conditions, okay? But here we are in a non-critical domain, so we know that the energy is decreasing to 0. We knew that yesterday, but now we have even a Lyapunov function to prove that. But here it's not needed, okay? So there is no other condition because we start with a KdV which is already stable when we decouple from the ODE just by force, okay? Well, of course, here we have to consider, as we have already done, this y tilde is just y minus the quasi-static part of the solution, okay, which was minus 2f of times a times z, and we obtain a system as the previous one with extra terms, as usual when we apply this method for the wave, for the KdV, or for first order hyperbolic system. And all that we obtain, in fact, always the same equation, but with extra source term that we have to deal with, okay? And here we have again the result that, in fact, using the same Lyapunov function, we're able to prove that this system is exponentially stable if epsilon is small enough, under the condition that b minus ac is less than 0. Okay. Nice. And of course here, well, not of course, but we can look at what we call a Tikhonov theorem that we made. Also, we made a theorem like that for the wave equation, wave ODE system. And here, of course, there are more conditions which are similar to the finite dimensional case or to the case of any value of epsilon, okay, in order to have that under some condition on the coefficients, okay, the solution y can be approximated by the boundary layer system plus the quasi-static solution, okay, and of course, well, z can be approximated by the reduced order system z bar, okay? You can prove that, and again, the proof, I didn't put it here. No, I didn't put here, but it's again dealing with the same Lyapunov function, well, Lyapunov function in this case, okay, with for PDEs, and be able to track all the terms, the coefficient, the epsilon everywhere, They are very easy computation, but you have to be just careful with tracking all the terms everywhere. Okay. This is our result with swan marks. And here, I don't know if I put it. Yeah, just to comment a little bit. We are almost ending. Okay, we are finishing here. I will take 10 minutes less just to compensate you. Okay, and so here we have the fast ODE with the KdV equation. Okay, and here that's the singular perturbation method works. And yes, but the proof has to be has some changes, of course, but the approach is the same. Okay, here we use these two systems. We obtain the reduced order system, the boundary layer system for this slow KdV fast ODE system. Okay, and here we obtain for the ODE is also very simple here. Again, we have just b less than 0 in order to have this reduced order system stable, to make it stable. And for the PDE, for the KdV equation, we get this one, which is not obvious what is the behavior of this system. In fact, you know, is a linear KdV equation with homogeneous Dirichlet boundary condition, but there is a condition here that relating both Neumann condition and both left. Okay. For instance, here we know that if AC over B is -1, so the condition is kind of periodic one for the derivative. Okay, the system conserves the energy. Okay, we can prove that very, very easily. And here, you know, we have a coefficient. So the condition for the stability, and that comes from a paper by Binjuzan in '94, is that the modulus of this coefficient has to be less than 1. Okay, is, you know, kind of the same boundary, the same condition that we obtained in the first day for the transport equation. When if for the transport equation we put some condition like this one, so what we put as control is a constant k times what we see on the other end of the interval, the system is exponentially stable, and we can prove it with the Lyapunov functional with this exponential minus mu x term. Okay, so here the proof here by Binjuzan, they compute eigenvalues and they make that approach in order to see what's happening with the stability. So nice problem. Here, well, in that case, when we put the epsilon on the ODE, we are able to deal with a simpler Lyapunov function. Okay, we don't have to introduce this operator m. Okay, we just put this Lyapunov function for the KdV and just the energy. Okay, it looks like it has the right sign here, but b is less than 0, so this is positive. Okay, yeah. Here at the end of the day, we obtain very similar results as the one I told you for the other system. Okay, but just to point it out that here we need more regularity of the solutions, H3. That's the reason of that is that here at some step we obtain that C tilde is Z plus this trace of Y. And you know, we have to obtain the equation for Z tilde. So we have to derivate in time. So we need more regularity in order to make all that possible. And a Tikhonov type theorem can also be obtained, but it's not that nice to write. It's very similar to the previous one. Okay? And just to finish my lectures, I would like to just mention 2 papers where same kind of approach is made, just to mention them. Okay, the first one is a paper by Gonzalo Arias, Swan Mars, and myself. Gonzalo Arias is a PhD student of mine working in Chile, and co-directed by Swan-Marx, okay, in Nantes in France. So here we have made the same approach that I have explained you today and in previous lectures in order to consider a system where we have a wave here. U is a wave. Here we have the same boundary conditions as before, where we know that there is this Lyapunov function that we can work with, okay? And here we have a coupling P at 0, where P is solution of a heat equation, okay? We have this epsilon, so we have a fast heat equation with a wave equation coupling, okay? We have studied, of course, in the theorem, I didn't tell you anything about that, but there are, of course, well-presented results. And of course, here, stability for, first of all, for any value of epsilon, and then to look at the case of a small epsilon using these singular perturbation methods, okay? And here, the approach is the same as here in the sense that using Lyapunov functions. And another paper by, again, Gonzalo Arias, Swan-Marx, and Guillermo Santi, okay? Guillermo Santi from Super Lake in France, okay? They have studied this system here, which is an ODE for Z coupled to the PDE, a first order hyperbolic PDE for Y, okay? In fact, well, with this coupling, okay? This system 24 has been already studied by Tang and Manzanti, okay, in a paper in Automatica 2017. In fact, that's the paper where I took an example that I'll show you in the first lecture, okay, where a gas was moving through a tube, okay. In that original paper by Tang and Manzanti, they take a look at this system by using the singular perturbation method, okay, and using Lyapunov approach as we have done these days, okay. So the new idea of Arias, Marx, Masanti in this conference paper in CDC, they are finishing the redaction of a journal paper with these results, okay. Instead of Lyapunov approach, they use a frequency approach. Let's say that they go and compute the eigenvalues of the system, okay? And in fact, they can improve the conditions for stability that Tangamasanti obtained in their paper. They improve it, and they can finally say that the stability condition for the SAS system are the same that are sufficient conditions for the full system, okay? In this paper, some stronger condition has to be imposed, okay? So using this frequency approach, as in a general statement, with eigenvalues, we can see better in some situation what's happening, okay? But it's limited to some situation, for instance, constant coefficient and system data, okay? So that's all I have to tell you, so thank you.
Thank you for the nice talk, Eduardo. So now I ask the audience if they have a question, they can ask directly to Eduardo, and also the online participants, if they have a question, they can ask.
For the new Lyapunov function, you added a new term. Is there some motivation can you give, please? They added, the paper use M with the integral operator M.
Okay, because I was thinking that for the...
Epsilon M Y minus Z, that was the term.
Yeah, well...
Any motivation, how did they got...
Where the motivation come from, let me... here from this... yeah, for instance, here we have this... that's here, no. Yeah, no, for instance, this is even for the OD, okay? For the motivation is that, well, we know that here, the y tilde function was already exponentially stable, so we have a Lyapunov function for that, okay? So this comes from this system, what is this method that's called forwarding theorem in the same forwarding approach, in the sense that when you have a stable system, and you add a kind of integrator, you add another variable coupled to this one, okay? So if you already have a Lyapunov function for the first equation, and you add the second one, what kind of Lyapunov function approach you can expect to the full system? And in fact, well, a first normal step will be to just add the energy of the norm of the second variable. Here, the normal thing to think first was to consider V as y tilde, I forgot a square, y tilde square plus Z square, okay, in terms that the energy of both parts. But here, you know, you expect that there are some link between Z and Y. So the evolution of Z is not free, have to be approached by something depending on Y.
And in the last slide, you mentioned they go to the frequency domain and then.
Well, more than applying Laplace transformation, they just, you know, write the system as with matrices, and we see at the location of the poles of the eigenvalues of the system.
But when they come back, they have to come back to 0, 1 because the x was in a bounded interval.
Yeah, no, but it's just on time. They
Time
look at the,
oh.
yeah. So they can do it just to look at the eigenvalues in time. Yeah.
Okay, thank you.
I have a question. So for large values of epsilon, do you have instability?
For
large values of epsilon.
Epsilon.
Yeah.
Yeah, in the, for instance, here in the case that for the KDVOD, yeah, but you have to be more restrictive on the conditions on the coefficients, on the other coefficients. But here, for instance, for any value of epsilon, you can find condition on the coefficients in order to get stability.
Yeah, but my question was instability.
Instability.
Yeah.
Okay.
So
yeah. Normally, in fact, you can pick the right coupling term, for instance, in order to get stability.
Is it possible to give some necessary and sufficient conditions? Necessary and sufficient conditions on the coefficients to get the stability.
Yeah. Well, for instance, here in the case of the, for instance, for the transport equation, yes. For the wave equation for instability, yeah, it's not clear for me. Here is no, neither. Okay, sufficient and necessary condition.
Okay, if there is no other question, so thanks Eduardo again for the nice lecture series.
Thank you very much.